In the twilight hours of the 20th century, as the internet was still finding its adolescent footing and the world remained skeptical of digital commerce, a young South African entrepreneur was already thinking in systems most people couldn't yet comprehend. His name was Elon Musk, and what would unfold over the next 3 decades would fundamentally rewrite the trajectory of human innovation. The year was 1995, when Musk and his brother Kimball launched Zip2, a web software company that provided business directories and maps for online newspapers. It seemed modest by today's standards, a simple digital tool in an era when the internet itself was still considered something of a curiosity. But what separated Musk from countless other entrepreneurs grinding away in garages and startup incubators was something more fundamental. He wasn't building for profit. He was building for purpose. He was thinking about systems, about scale, about what humanity needed rather than what the market wanted. When Compaq acquired Zip2 for approximately $307 million in 1999, most entrepreneurs would have celebrated their exit. Musk, instead, immediately turned his attention toward what he perceived as the next evolutionary leap: digital payments. While the dot-com bubble was inflating around him, while fortunes were being made and lost on the mere speculation of internet-related companies, Musk founded XCOM in 1999. The platform was designed to facilitate online financial transactions, a vision so ahead of its time that even venture capitalists struggled to articulate why it mattered. XCOM merged with Confinity in 2000, a critical moment that would set the trajectory for everything that followed. The merged company would eventually become PayPal, which sold to eBay for $1.5 billion in 2002. But more importantly, this experience taught Musk something profound about the intersection of technology, financial systems, and human behavior. He learned that the algorithm, the underlying code and logic that determines how systems operate, could be harnessed to reshape entire industries. What few people understood at the time was that Musk wasn't chasing wealth or status in the conventional sense. He was observing something that venture capitalists and business schools had largely missed: that transformative technology required thinking in terms of first principles rather than incremental improvement. It required asking not, "How can we do this better?" but, "Why are we doing this at all? What problem are we actually solving?" In May 2002, Musk founded SpaceX with $100 million of his early fortune and became the company's CEO and chief engineer, with the explicit mission of reducing the cost of space travel and making humanity a multi-planetary species. According to corporate filings, SpaceX was incorporated on March 14, 2002, though operations began in earnest in May of that year. The aerospace establishment responded with something between amusement and contempt. Lockheed Martin, Boeing, and other defense contractors had spent decades building rockets that cost hundreds of millions of dollars. The economics seemed immutable, locked into place by decades of government contracts, established supply chains, and engineering conventions. When Musk announced that SpaceX would develop and launch rockets for a fraction of that cost, the response was nearly universal dismissal. What these established players didn't recognize was that Musk wasn't trying to optimize the existing system. He was fundamentally rethinking it. Traditional aerospace contractors had built their rocket programs around a specific algorithm of production: expensive components, limited production runs, high unit costs. SpaceX approached the problem differently, applying manufacturing principles derived from the automotive and consumer electronics industries. They designed for mass production, for iteration, for learning through rapid prototyping. The algorithm underlying SpaceX's approach was revolutionary in its simplicity: build, test, fail fast, learn, improve, repeat. It was the same philosophy that had driven Silicon Valley software companies, but applied to physical objects of staggering complexity and expense. Early SpaceX rockets failed spectacularly. Falcon 1's first 3 launches resulted in total loss, but each failure contained data. Each explosion was a teacher. Early SpaceX rocket failures were significant. Falcon 1's first 3 orbital flight attempts, 2006-2008, resulted in complete loss of vehicle. The 4th attempt in September 2008 succeeded, proving that a private company could successfully reach orbit. However, It would take until June 4, 2010, for Falcon 9 to achieve its first successful orbital flight, reaching low Earth orbit and further validating SpaceX's approach. More importantly, these milestones demonstrated that the algorithm of rapid iteration and data-driven improvement could work at the scale of rocket science. Simultaneously, Musk had invested in Tesla Motors in February 2004 as the company's largest investor, becoming chairman of the board. Tesla had been incorporated on July 1, 2003, by founders Martin Eberhard and Mark Tarpenning in San Carlos, California. Musk's investment of $635 million out of the $6.5 million Series A funding round gave him significant influence over the company's direction. Musk's involvement with Tesla represented something more than simply building electric cars. It represented a fundamental reimagining of what an automobile manufacturer could be. Traditional automakers had built their business algorithms around dealership networks, service centers, and a complex supply chain optimized for internal combustion engines. Their incentive structures, their engineering priorities, even their corporate cultures were aligned with this system. Tesla's algorithm was different. Vertical integration, direct sales, software-driven updates, battery-centric design, over-the-air updates that could continuously improve vehicles after purchase. These weren't just different business decisions. They represented a completely different conceptual approach to what a car could be. When Tesla released the Roadster in 2008, the same year SpaceX achieved its first successful Falcon 1 orbital launch, the electric vehicle was perceived as a boutique toy for wealthy early adopters. The battery technology was expensive, the charging infrastructure didn't exist, and the automotive establishment was skeptical that electric vehicles could ever achieve meaningful performance. Yet Musk had a longer-term algorithm in mind. The Roadster wasn't the final product. It was proof of concept. By 2010, Tesla released the Model S, and something shifted in the market's perception. Here was a car that combined performance, range, and luxury in a package that challenged everything the automotive industry had built. The algorithm had proven that electric vehicles weren't a compromise. They could actually be superior. What emerges when you examine Musk's trajectory across SpaceX, Tesla, and later ventures like Neuralink and the Boring Company is a consistent underlying algorithm, a methodology that repeats regardless of industry or technical domain. Understanding this algorithm is essential to understanding why Musk has been able to successfully challenge established industries while most entrepreneurs fail. The first principle in this algorithm is radical rethinking of fundamentals. When entering a new domain, Musk doesn't ask, how do existing players operate? He asks, what are the fundamental constraints, and are they really constraints or merely conventions? When he looked at rockets, he recognized that launch costs were high not because of immutable laws of physics, but because of the algorithm of aerospace production. When he looked at automobiles, he recognized that inefficiency was baked into the supply chain and business model, not required by the technology itself. This principle of rethinking fundamentals was demonstrated most clearly in SpaceX's approach to rocket reusability. The entire aerospace industry had built an algorithm around single-use rockets. A rocket launches once, its first stages fall into the ocean, and that's the end of that vehicle. Replacement rockets cost hundreds of millions of dollars each. Musk looked at this and asked a simple question. Why should rockets work like airplanes work? We don't throw away airplanes after a single flight, but instead like an entirely expendable commodity. This single question led to the Falcon 9's revolutionary first-stage landing capability, which achieved successful autonomous landings in 2015 and has since landed hundreds of times. The second principle is the obsessive focus on unit economics and marginal cost reduction. Traditional industries measure success through profit margin percentages. A 30% profit margin on a luxury car is considered excellent. But Musk's algorithm prioritizes absolute cost reduction at scale. If you can reduce the cost of a rocket launch from $65,000 per kilogram to $1,500 per kilogram, you don't just improve the business, you transform the entire industry. You make access to space economically viable for uses that were previously impossible. This obsession with cost has driven Tesla's evolution more than almost any other factor. The Model 3, released in 2017, was designed from the beginning around a different algorithm than the Model S and Model X. It wasn't a luxury vehicle compromised for the mass market. It was engineered from the ground up around the question: what is the minimum viable cost to produce an electric vehicle while maintaining sufficient quality and performance? The answer involved not just engineering changes, but manufacturing innovations, supply chain transformations, and willingness to challenge conventions about how cars should be built. The third principle is the integration of software and hardware in ways that were previously separated. In the traditional automotive industry, a vehicle was largely a physical product. Software existed to support it, engine management, infotainment systems, but it was peripheral to the core product. Tesla's algorithm integrated software into the fundamental value proposition. Over-the-air updates aren't a feature. They're the foundation of the business model. A Tesla vehicle becomes more valuable over time without requiring physical maintenance or replacement. The single principle has created a competitive moat that traditional automakers still struggle to comprehend. Perhaps the most sophisticated element of Musk's algorithm is understanding and leveraging what might be called scale multiplication effects. How investments in one domain can compound across multiple domains in ways that weren't previously possible. Tesla's expansion into energy storage and solar represents one manifestation of this principle. By developing batteries at scale for vehicles, Tesla gained manufacturing expertise and supplier relationships that made energy storage production economically viable. The algorithm of manufacturing that had been optimized for automotive batteries could be repurposed for stationary storage. The scale of production created unit cost advantages that made energy storage products competitive with traditional generators and grid-scale battery systems. SpaceX's reusable rocket program creates similar multiplication effects. Each successful landing of a first stage generates data about propulsive landing dynamics, aerodynamic loads, and materials stress that informs the design of the next vehicle. Each reuse reduces the effective cost of access to orbit, which makes possible more frequent launches, which generates more data, which drives further cost reduction. The algorithm creates a compounding advantage curve that separates SpaceX's cost trajectory from the aerospace industry's static cost structure. The Boring Company represents perhaps the clearest example of how Musk applies this multiplication principle across seemingly unrelated domains. The company was founded in 2016 with the mission of solving traffic congestion through underground transit tunnels. The first principle approach to the problem questioned why tunnel boring machines are so expensive and progress so slow. Musk's algorithm applied manufacturing efficiency principles. If you increased the speed of tunnel boring equipment and reduced its cost through manufacturing optimization and materials innovation, you could fundamentally change the economics of urban infrastructure. What connects SpaceX, Tesla, and the Boring Company is not that they're in related industries. It's that they all apply the same underlying algorithm. Identify an industry with high costs and slow improvement, question the fundamental constraints driving those costs, apply manufacturing innovation and supply chain optimization to reduce costs, use the cost advantage to increase scale, and reinvest the scale advantage into further innovation. The reason Musk has been able to disrupt multiple major industries is that he doesn't think in terms of individual products. He thinks in systems. When most entrepreneurs see an opportunity to build a better car, Musk saw the opportunity to build a complete ecosystem that would transition humanity from fossil fuels to sustainable energy. When most people saw a commercial space industry, Musk saw the foundation for making humanity multiplanetary. This systems thinking approach manifests most clearly in Tesla's energy business. The company didn't simply develop electric vehicles and hope the charging infrastructure would develop naturally. It invested heavily in its own charging network. It moved into energy storage and solar power. It developed software platforms that could integrate vehicles, home energy systems, and grid-scale storage into a coherent whole. The algorithm wasn't build great cars. It was create an energy transition ecosystem in which great cars are essential components. Similarly, SpaceX's development of full-stack capabilities, from engine manufacturing to avionics to ground infrastructure, represents systems thinking at the organizational level. Rather than being a systems integrator that outsourced components to traditional aerospace suppliers, SpaceX built most capabilities internally. This vertical integration is expensive and risky, but it provides something that traditional contracting doesn't: alignment of incentives and unified optimization. When your suppliers are external contractors, optimizing one component might compromise system performance. When you control the full stack, you can optimize across the entire system architecture. The ambition of this systems thinking approach reaches its zenith in Musk's vision for Mars colonization. This isn't simply about building rockets that can reach Mars, although that's essential. It's about designing a complete transportation system, life support architecture, power generation system, and manufacturing infrastructure that could support a self-sustaining settlement. Starship, SpaceX's next-generation super heavy lift launch vehicle, represents the keystone technology, but Musk's algorithm extends far beyond rocket design to encompass every element of the Mars infrastructure. Throughout Musk's career, one phrase appears again and again: first principles. When discussing why SpaceX could achieve what established aerospace companies couldn't, he invariably points to thinking from first principles rather than accepting inherited assumptions. When explaining Tesla's manufacturing innovations, he emphasizes going back to fundamentals rather than following industry convention. First principles thinking means refusing to accept that this is how things have always been done, as a sufficient justification for continuing to do them that way. In rocketry, it meant questioning why solid rocket boosters, expensive, dangerous, and single-use, remained the standard when alternative propulsion approaches might work. It meant asking whether launching from central facilities made sense, or whether distributed launch sites might be more efficient. It meant challenging every assumption about what a launch operation should be. In automotive manufacturing, first principles thinking led Tesla to question some of the foundational assumptions that had driven automotive production for decades. Traditional automotive plants were organized around specialized stations: body welding, paint application, assembly, testing. This separation made sense under certain economic conditions, but constrained flexibility and created inventory buffers between stations. Tesla's manufacturing algorithm experimented with different organizational models, integrating some processes, automating others, and continuously questioning whether the traditional sequential flow made sense for a company trying to maximize throughput and quality simultaneously. Manufacturing innovation at Tesla extended to questioning whether the conventional division between design and manufacturing made sense. Traditional automotive companies had separate design and manufacturing organizations, with manufacturing tasked with implementing designs created by engineering teams. Tesla's algorithm integrated these functions more completely, ensuring that manufacturability informed design decisions from the earliest stages, rather than discovering manufacturing constraints late in the development process. The gigafactory concept represents the ultimate expression of this manufacturing-centric algorithm. Rather than building vehicles in traditional distributed factories optimized around geographic markets, Tesla centralized battery production with vehicle manufacturing. The reasoning was that batteries represent the most cost-intensive component of electric vehicles, and the greatest opportunities for cost reduction exist at the manufacturing process level rather than the component design level. By controlling battery production completely and optimizing the manufacturing process continuously, Tesla could drive battery costs down far more effectively than if it relied on external suppliers competing in an open market. When Tesla announced intentions to move into the automotive market, established automakers responded with something between dismissal and contempt. Toyota, General Motors, Ford, Volkswagen, companies with decades of experience, supply chains optimized through generations of learning, manufacturing facilities built specifically for automotive production, viewed Tesla not as a threat, but as a curiosity. An electric car maker with no manufacturing experience, no dealer network, no established customer service infrastructure. The competitive advantages these established players possessed seemed immutable. Yet within a decade, Tesla's market capitalization had surpassed that of General Motors and continued climbing. Its profit margins on vehicles often exceeded 25%, while traditional automakers struggled to achieve single-digit margins. Its customer satisfaction and loyalty scores exceeded those of luxury brands. The competitive advantage that seemed certain proved fragile. The fundamental reason established competitors couldn't compete wasn't technical, Toyota, General Motors, and Volkswagen all possess world-class engineering talent. They understood battery technology, electric motors, and advanced manufacturing. The issue was algorithmic. Their entire organizational structure, incentive system, and decision-making processes were optimized around the internal combustion engine. Asking these organizations to transition to electric vehicles was asking them to undermine the value of their existing investments, challenge their existing supply chain relationships, and compete against companies with no legacy constraints. This organizational inertia is often called the innovator's dilemma. Established companies struggle to disrupt their own markets because doing so threatens existing business models and installed investments. But Musk's algorithm sidesteps this dilemma entirely by not trying to work within existing systems. Tesla didn't try to convince established automakers to transition to electric vehicles. It built a company designed from the ground up around electric propulsion, avoiding the legacy constraints that would inevitably compromise any transition effort by existing companies. The competitive advantage compounds over time as Tesla accumulates data about battery manufacturing, electric motor performance, thermal management, and real-world vehicle operation. Each vehicle sold generates telemetry that informs future design decisions. Each manufacturing cycle reveals opportunities for cost reduction and quality improvement. Each supercharger deployed gathers data about charging patterns, power delivery requirements, and customer behavior. This data becomes a competitive moat that widens as Tesla's installed base grows. SpaceX faces similar competitive dynamics. Traditional aerospace companies tried to compete by building their own reusable rockets or developing new launch systems. Some efforts are ongoing and may eventually produce results. But SpaceX's algorithm advantage, having accumulated data from hundreds of landings, optimized the manufacturing process through scale production, and achieved cost structures that traditional contractors simply cannot match, makes catching up extraordinarily difficult. Decades of single-use rocket operations created no data about what successful reuse required. SpaceX's algorithm of rapid iteration and learning from every launch has created advantages that compound with each successful mission. In traditional industries, competitive advantage often derived from physical assets. Factories, infrastructure, raw materials, patent protections. In Musk's algorithm, competitive advantage increasingly derives from software, data, and organizational learning. Tesla's over-the-air update capability represents this shift more clearly than almost any other innovation. A traditional automobile is essentially static from the moment it leaves the factory. Its capabilities are fixed. Performance characteristics, safety features, functionality, all defined at manufacturing time. Tesla's algorithm made vehicles dynamic. A Tesla receiving a software update could gain new features, improve performance, or enhance safety, all without requiring the customer to visit a service center or replace any physical components. This capability creates a competitive advantage that's difficult to match because it requires thinking about vehicles as software platforms rather than mechanical artifacts. It requires designing vehicles with sufficient computing power to support future updates. It requires building organizational processes that can develop, test, and deploy software updates across hundreds of thousands of vehicles simultaneously. It requires rethinking how manufacturing tolerances and component selection interact with software optimization. The data advantage is equally significant. Every Tesla vehicle generates continuous telemetry about how it's being driven, environmental conditions it encounters, charging patterns it follows. This data becomes training material for machine learning systems that inform everything from energy management algorithms to autonomous driving development. Traditional automakers, with their distributed dealer networks and less connected vehicles, simply don't have access to this continuous stream of operational data from their customer bases. SpaceX's data advantage manifests differently, but with similar competitive implications. Every Falcon 9 launch generates precise data about engine performance under various atmospheric conditions, rocket behavior during ascent, aerodynamic loads during descent, and landing system performance. This data has been accumulated across hundreds of launches, creating a training dataset of extraordinary richness for optimization systems. Each launch is simultaneously an operational mission generating revenue and a continuous experiment advancing engineering understanding. Beyond Tesla and SpaceX, Musk has begun applying his algorithm to domains that few other entrepreneurs have dared enter: the direct interface between human brains and computers. Neuralink, founded in 2016, represents perhaps the most ambitious application of Musk's systems thinking approach. The conventional approach to brain-computer interfaces has been through established neuroscience research institutions and medical device companies operating incrementally, conducting safety studies, and advancing understanding one step at a time. Musk's algorithm approached the problem differently. If you could develop implantable electrodes with sufficient density and signal quality, if you could create flexible materials that wouldn't trigger immune rejection, if you could develop software that could interpret neural signals reliably, and if you could design neurosurgical robots that could implant these devices safely, you could create something transformative: a direct bandwidth connection between human cognition and computation. The first principles approach questioned many inherited assumptions about how brain-computer interfaces should work. Rather than accepting that existing electrode technology was acceptable, Neuralink pursued novel approaches. Rather than assuming that FDA approval timelines were immutable, Musk engaged directly with regulators to understand what would be required for approval. Rather than assuming that academic neuroscience labs were the appropriate venue for development, Neuralink built its own research and manufacturing capabilities. The competitive advantage algorithm underlying Neuralink extends beyond pure technology. It includes organizational structure optimized for rapid iteration, design for manufacturability built in from the earliest stages, and willingness to take risks that academic institutions or traditional medical device companies would consider unacceptable. The first human implant occurred in January 2024, an extraordinarily rapid timeline from technology development to human deployment. The Boring Company and Musk's work on Hyperloop concepts represent the same algorithm applied to infrastructure problems. Both represent first principles approaches to challenging physical constraints that have seemed immutable for decades. Traditional tunnel boring progresses at approximately 30 to 50 meters per day. Boring machine costs reach hundreds of millions of dollars. The algorithm underlying these constraints isn't optimal, it's historical. Tunnel boring machines have been evolved incrementally over decades, with each improvement building on previous designs. Musk's first principles approach questioned whether this evolutionary pathway was actually optimal or merely historical. Could you increase boring speed through different excavation approaches? Could you reduce machine costs through simplified designs and distributed manufacturing? The Boring Company's approach involved developing simpler boring machines, optimizing the excavation process, and reducing operational complexity. While commercial adoption has been limited, the exercise of rethinking tunnel construction from first principles has proven valuable in its own right. It demonstrated that the algorithms constraining tunneling speeds and costs aren't fundamental, merely conventional. Perhaps the most significant domain where Musk is applying his algorithmic thinking is artificial intelligence. Having founded OpenAI in 2015 as a nonprofit research institution focused on ensuring AI development proceeded safely and benefited humanity broadly, Musk has consistently emphasized that AI represents both extraordinary opportunity and genuine existential risk. The algorithm he's advocated for involves developing AI systems that remain interpretable and aligned with human values, rather than creating increasingly powerful black box systems whose decision processes can't be understood or controlled. This emphasis on interpretability and alignment represents a first principles approach to AI development that differs markedly from the dominant industry trajectory of simply scaling models and hoping alignment emerges as a byproduct. Neuralink itself can be understood partly as an AI-adjacent initiative. The idea being that as artificial intelligence becomes increasingly sophisticated, humans will need direct neural interfaces to interact with AI systems at bandwidth sufficient to remain meaningfully engaged with them. The algorithm suggests that the future won't be humans passively receiving information from AI systems, but rather humans and AI systems in tight feedback loops through high-bandwidth neural interfaces. The cumulative impact of Musk's algorithmic approach to innovation has been to reshape multiple industries at fundamental levels, not incrementally, but through discontinuous disruption. The automotive industry, previously locked into 20 to 30-year product development cycles and conservative approaches to new technologies, has been forced to accelerate electric vehicle development timelines dramatically. Traditional automakers that had planned gradual transitions to electrification found themselves racing to avoid market irrelevance. The aerospace industry, similarly locked into slow development cycles and expensive single-use systems, has been disrupted by SpaceX's demonstration that faster iteration, rapid learning, and reusable systems could achieve what had seemed impossible. Competitors have responded by attempting to develop reusable systems of their own, but SpaceX's data advantage from hundreds of landings remains overwhelming. Beyond these direct industrial impacts, Musk's algorithmic approach has influenced how entrepreneurs and companies across numerous industries think about disruption, first principles, and the possibility of fundamental transformation, rather than incremental improvement. Yet the analysis would be incomplete without acknowledging the risks and potential downsides of Musk's approach. His first principles methodology and willingness to challenge conventions has led to extraordinary achievements, but it has also occasionally led to overconfidence and misjudgment. Tesla's manufacturing challenges during the Model 3 ramp are instructive. Musk's algorithm of aggressive timeline setting and willingness to operate at the edge of feasible manufacturing sometimes created crisis conditions that stressed the organization severely. His public statements have occasionally moved into territory that risks regulatory scrutiny or market confidence. His acquisition of Twitter and subsequent attempts to reshape it around first principles thinking generated enormous controversy and raised questions about whether his algorithmic approach works in all domains or is fundamentally limited to technology and manufacturing. The question of whether first principles thinking can be applied effectively to human organizations and social systems differently than it applies to physical engineering problems remains open. Organizational culture, human psychology, and institutional constraints operate according to different rules than physics and chemistry do. Yet stepping back from specific controversies and challenges, the historical significance of Musk's algorithmic approach is becoming increasingly clear. He has demonstrated that industries that appeared locked in place, constrained by immutable economics, inherited infrastructure, and incumbent competitive advantages could actually be fundamentally disrupted by entrepreneurs willing to question basic assumptions and think from first principles. This insight has implications extending far beyond automotive or aerospace. It suggests that numerous industries currently considered stable and resistant to disruption, healthcare, energy production, agriculture, infrastructure, might be vulnerable to similar algorithmic disruption if entrepreneurs could identify the fundamental constraints that actually represent choices rather than immutable laws. The algorithm Musk has applied repeatedly: identify industry constraints, question whether they're fundamental or merely conventional, apply manufacturing innovation and vertical integration to reduce costs, leverage data and software to create sustainable competitive advantage, think in systems rather than products, provides a template that other entrepreneurs and organizations are beginning to apply. The pattern Musk has established raises a crucial question. Could similar algorithmic approaches reshape other industries? Before exploring that possibility, we must acknowledge a historical reality. Technological prediction has a poor track record. This matters because it frames what follows not as prophecy, but as informed speculation grounded in demonstrated successes and acknowledged uncertainties. In 1970, the Club of Rome predicted that the world would run out of oil within a decade. The prediction was wrong not because the analysis was flawed, but because it underestimated how innovation responds to scarcity. Higher oil prices incentivized efficiency improvements and exploration of new reserves. The pattern was consistent. Specific resource constraints that seemed immutable proved addressable through technological innovation and economic adjustment. Similarly, in 2000, digital utopians predicted that the internet would eliminate geographic constraints on business, that remote work would become universal, and that cities would depopulate. Instead, the internet's primary impact has been to concentrate wealth and talent in specific geographic locations: Silicon Valley, New York, Beijing. The technology didn't produce the predicted future. Human behavior and institutional constraints proved more powerful than technological capability alone. This historical pattern matters. Technological capability and actual adoption are not the same thing. A system can theoretically work while remaining economically unviable, regulated into impracticability, or rejected by users for reasons engineers didn't anticipate. One possibility is that Musk's algorithmic approach could transform urban transportation. The elements exist: Tesla's autonomous driving technology, the Boring Company's tunnel infrastructure, optimized urban planning through data analysis. If all these components matured simultaneously and achieved the cost reductions theoretically possible, cities could be restructured around distributed mobility systems rather than static traffic infrastructure. However, significant counter-arguments exist. Technical limitations. Autonomous vehicles have encountered problems that engineers in 2012 didn't anticipate: edge cases, adversarial weather, unpredictable human behavior. The gap between controlled testing and real-world deployment remains substantial. Years of development have proven the problem harder than initially expected. Regulatory friction. Cities don't operate on first principles thinking. They operate on centuries of accumulated law, established property rights, and political constituencies invested in current infrastructure. Building tunnel networks requires government coordination that the Boring Company has not successfully demonstrated at scale. Regulatory approval processes move slowly, not quickly. Economic viability. Current ride-sharing services haven't achieved profitability despite operating at scale. The assumption that autonomous vehicles would suddenly make this business model profitable remains unproven. Actual operational costs, maintenance, energy, infrastructure, might not achieve the theoretical minimums. User resistance. People have persistent preferences for personal vehicles, established driving patterns, and skepticism of unfamiliar systems. Behavior changes slowly even when superior alternatives exist. This isn't a technical problem, it's a social one. The transportation scenario is plausible but faces genuine obstacles that aren't primarily technological. Tesla's movement into batteries, solar, and grid management suggests a possible future where energy generation becomes distributed, storage becomes ubiquitous, and centralized fossil fuel infrastructure becomes economically obsolete. If battery costs continue declining, if renewable generation scales as currently projected, and if grid management software achieves the efficiency improvements theoretically possible, this transformation could occur. Yet counter-arguments are equally substantial. Infrastructure lock-in. Centralized power generation benefits from massive existing infrastructure investments. Utilities have legal monopolies in many regions and strong political constituencies. Displacing this requires not just superior economics, but regulatory change, which faces entrenched opposition. Intermittency problems. Solar and wind generation are intermittent. This requires either massive battery storage, geographic distribution that reduces transmission efficiency, or continued reliance on backup generation. The assumption that these problems have cost-effective solutions remains unproven at the scale global energy systems require. Material constraints. Scaling battery production to power. Global civilization requires minerals in quantities that might not be available. Lithium, cobalt, and rare earth elements face supply constraints that energy transition plans often underestimate. Political economy. Energy transitions involve geopolitical considerations: oil-producing nations, coal-dependent regions, established energy companies that create resistance independent of technology merit. The 2022 energy crisis in Europe demonstrated how quickly political factors can undermine even well-planned transitions. The energy decentralization scenario has genuine momentum, but encounters real constraints that technical excellence alone cannot overcome. SpaceX's demonstrated ability to reduce launch costs from roughly $65,000 per kilogram to approximately $1,500 per kilogram opens theoretical possibilities: orbital manufacturing, asteroid resource extraction, space-based solar power. If launch costs continued declining, and if manufacturing and microgravity proved economically viable, space could transition from science destination to economic frontier. However, substantial uncertainties exist. Profitability unproven. No space-based manufacturing has achieved commercial viability. The theoretical advantages of microgravity manufacturing haven't translated into products customers want to buy at prices that cover costs. Decades of research haven't produced a single profitable space manufacturing facility. Regulatory limitations. Space access is governed by international treaties that create barriers to resource extraction. Political complications around space militarization and national sovereignty could create regulatory restrictions that preclude commercial space development. Technical challenges. Operating manufacturing equipment in vacuum, at temperature extremes, with minimal human presence and under radiation exposure, creates engineering problems that remain largely unsolved. The assumption that these are primarily cost problems rather than fundamental technical barriers might be incorrect. Economic competition. SpaceX's cost reductions are impressive, but Earth-based manufacturing is also improving. The assumption that space-based production will become cheaper than terrestrial manufacturing remains speculative. Space industrialization is conceivable, but faces technical and economic barriers that current progress doesn't necessarily overcome. Neuralink's development of high-bandwidth neural interfaces could theoretically transform human-computer interaction. If the technology matures, gains regulatory approval, and proves safe across millions of users, direct neural communication with AI systems could enhance human cognition in profound ways. Yet this scenario faces particular challenges. Biological uncertainty. The brain is incompletely understood. Neural interface technology rests on foundations that neuroscience is still building. Scaling from small experimental implants to safe, reliable systems for millions of people encounters biological complexity that engineers can't fully predict. Ethical concerns. Implanting devices in human brains raises concerns about privacy, security, cognitive autonomy, and consent that go beyond technical feasibility. Regulatory approval for neural interfaces will likely proceed much more slowly than for conventional medical devices. Security vulnerability. Any device creating direct neural-computer connection creates security risks unprecedented in scale. Hacking a smartphone is inconvenient. Hacking a neural implant could directly damage human cognition. The security requirements for this technology are qualitatively different from standard computing security. Adoption barriers. Even if the technology worked perfectly, adoption would face resistance. Most people are deeply skeptical of brain implants. Regulatory bodies will impose strict limitations. Commercial viability might remain limited to specific medical applications rather than broad consumer adoption. Neural augmentation is theoretically possible, but faces biological, ethical, and security barriers that may prove more significant than technical ones. What emerges from examining these scenarios is this. Musk's algorithmic approach has proven extraordinarily effective in aerospace and automotive because those domains have clear physical constraints, measurable performance metrics, and direct economic incentives for improvement. In these domains, first principles thinking combined with manufacturing discipline genuinely does overcome entrenched incumbents. However, when the same algorithmic approach encounters domains with complex regulatory environments, entrenched political interests, biological or fundamental technical uncertainties, user behavior and adoption barriers, multiple competing approaches with equal validity, the algorithm becomes less deterministic. Superior engineering doesn't automatically produce market success. Better technology doesn't automatically overcome regulatory obstacles. Demonstrating theoretical superiority doesn't automatically change behavior. Importantly, Musk's approach isn't the only way innovation occurs. Throughout technological history, transformation has happened through multiple mechanisms: regulatory change that incentivizes new approaches, gradual improvement through incremental innovation, user adoption driven by social factors rather than technical superiority, and distributed innovation across many organizations, rather than concentrated in single visionary companies. The electricity grid emerged not through one visionary's algorithmic thinking, but through competing approaches, regulatory innovation, social adoption patterns, and distributed capital investment. The internet emerged through decentralized development across universities and defense agencies, not through a single company's first principles approach. The transition away from horse-drawn carriages happened gradually through many companies, not through one transformative organization. Musk's approach is powerful, but not universal. Different industries and different challenges might require different solutions. The honest assessment is this: SpaceX and Tesla have demonstrated that algorithmic disruption is possible in specific domains under specific conditions. Whether that approach scales to other domains remains an open question. Whether other approaches prove equally or more effective remains unclear. The story of how Musk rewired the future isn't complete. It's ongoing and uncertain. SpaceX continues advancing toward Mars colonization. Tesla continues expanding its product line. Neuralink advances neural interface technology. But whether these efforts will produce the transformations that optimistic speculation suggests remains fundamentally unknowable until they actually occur, or fail to occur. The pattern has been established. Systematic first principles thinking combined with manufacturing discipline can overcome entrenched industries in domains with clear physical constraints and measurable metrics. Whether that pattern extends beyond those specific conditions remains one of the more important unanswered questions about how human innovation actually works.